In this lecture, we will be covering some more advanced examples of working with indeterminate forms. Recall L'Hopital's rule. If you have differentiable functions f and g, and you're looking at the limit as x goes to a of their quotient, and direct evaluation of limit of the top and the bottom yield indeterminate forms 0 over 0 or infinity over infinity, we can use L'Hopital's rule, which tells us that the limit of that quotient is equal to the limit of the quotient of the derivatives of the numerator and the denominator. There are some indeterminate forms, like say 0 times infinity, which we can rework to get into a form that would work to use L'Hopital's rule. And the reason why 0 times infinity is an indeterminate form is we want to think of things as racing. So if you have f of x, which is racing to 0, and g of x, which is racing to infinity as x goes to a, it's the rate at which f of x goes to 0 versus the rate at which g of x goes to infinity that will determine this limit. So you can get a limit of 0, you can get a limit of infinity, you can get a limit of some other finite constant depending on the rates at which these two f and g are moving towards their limits of 0 and infinity respectively. And what we notice is if we rewrite this multiplication as a division by a division, this can work in our favor. So think of the case where suppose f of x is going to 0 and g of x is going to infinity. If g of x is going to infinity, we can think of g of x as exploding. So that means 1 over g of x is going to 0. That means when we rewrite this multiplication as division by a division, we now have a numerator going to 0 and a denominator going to 0, which gives the 0 over 0 indeterminate form, which means we can use L'Hopital's rule. So, this example is an illustration of this. So in this case, we're looking as x goes to infinity. So this first term, this x, is going to infinity. And we note that x minus 1 over x plus 1 is going to 1 as x goes to infinity. Right? We have dominant term x and dominant term x in numerator and denominator. But natural log of 1 is 0. So the entire natural log term is going to 0. So we have an infinity times 0 indeterminate form here. So what we can do, we can rewrite this as the limit as x goes to infinity with the natural log term in the numerator. And instead of multiplication by x, we divide by 1 over x. And now we have a numerator going to natural log of 1 or 0, and we have a denominator going to 0. So we have the 0 over 0 indeterminate form, and we can thus use L'Hopital's rule to say that this is the limit as x goes to infinity of the derivative of the numerator divided by the derivative of the denominator. So for the derivative of the numerator, the derivative of natural log of this expression is 1 divided by this expression, or 1 over quantity x minus 1 over x plus 1, times the derivative of the inside. So the derivative with respect to x of x minus 1 over x plus 1. And in the bottom we have derivative of 1 over x, which we can rewrite as x to the minus 1. Thus, this becomes the limit as x goes to infinity. This first expression is x plus 1 over x minus 1. And then for this second term, we need quotient rule. So we have the denominator times the derivative of the numerator, which is 1, minus the numerator times the derivative of the denominator, which is 1, all over the denominator squared. Then this is divided by the derivative of x to the minus 1, which is minus x to the minus 2. Now the work is really algebra, because we need to simplify this expression. So this is the limit as x goes to infinity. We see x plus 1 cancels with one of the x plus 1 terms here. So in this expression in the overall numerator, we will have an x minus 1 and an x plus 1 surviving. So we have 1 over x minus 1 times x plus 1. And simplifying this expression here, we have 1 times x plus 1, which gives us x plus 1. And then we have minus x. And then we have a minus 1, so plus 1. We can then bring this negative x to the minus 2 up into the numerator, and that becomes negative x squared. We then see the x and the minus x here cancel, resulting in 2. And this expression becomes the limit as x goes to infinity of our numerator. We have a 2 and a negative x squared. So we have a minus 2x squared divided by this expression in the denominator, which we should FOIL out. So first, x times x gives us x squared. Outer, x times 1 is x. Inner, negative 1 times x is negative x, so those two will cancel. And then we have a 1 times minus 1, or minus 1. We then identify the leading term in the denominator, which is an x squared, and we divide every term in both the numerator and the denominator by that leading term. So this becomes the limit as x goes to infinity of minus 2x squared over x squared divided by x squared over x squared minus 1 over x squared. We simplify, and we get in the numerator a minus 2, in the denominator a 1 minus 1 over x squared. And using our limit laws, the limit of the quotient is the quotient of the limits. And then on the bottom, the limit of 1 is 1. The limit of this negative 1 over x squared as x goes to infinity. That term is approaching 0. And the result is an answer of negative 2. And when we look at that, we want to think about this. Does it make sense that this limit is negative? And it does, because you note that the x minus 1 over x plus 1 term here, we note x minus 1 over x plus 1. For x large, This numerator is a little bit smaller than the denominator, which means it's less than 1, which means the natural log of that x minus 1 over x plus 1 is negative, because we know our natural log function. If you have a value of x less than 1, which would be in this range here, that the natural log of that term is negative. So it makes sense to get an answer of minus 2. And it's important when you do these expressions, when you work these out, that you're always being careful to write your limit. Because if you don't write the limit, then the expression is different. You have a function rather than a limit. So this is a common approach when you have a 0 times infinity indeterminate form. And you also could have gone the other way. We could have kept x in the numerator and divided by this natural log term, in which case you would have had an infinity over infinity indeterminate form, and L'Hopital's rule would work there too, and you would get the same answer.